you're in Chemistry 30, your electrochem unit test might be coming up, and here is a really good resource for you to check out. It is from Quest A+, which is a website from the government that has old practice tests, or just practice tests in general for every diploma level class. You can either get a cumulative test like a practice diploma, or you could be unit specific. So this is a practice test or practice quiz for electrochem. So I have this here. So this is a really good review for you to study if you have your electrochem unit test coming up. So the very first question here is showing that you know oxidation and reduction. So you have 4 statements and asked which one would refer to oxidation. So if you are undergoing oxidation, we would write oil. That is going to be a loss of electrons. So if we went through it, the first one, sulfur forms stable ions by gaining electrons. Well, that's gaining, not losing, so that's not true. Magnesium forms stable ions by losing. That is true. The next one, oxidation numbers on iron change from 3 to 2. So if you're getting less positive, you are gaining electrons, so not that one. And then the next one, here we can see we are losing electrons because we're getting less negative. So our first answer is D in terms, oh, that's not the one I want. Sorry, it is B, 1 and 4. This next one here, looking at copper, we have an equation. There's some extra wording here, but just going straight to the question, it's asking what's happening to copper. So what I would do, just because it is asking about copper, is write out your oxidation numbers for just copper. So because of our fixed number of -2 on oxygen, copper is +2. And then over here, it stays +2 because it would be the same as its charge. So it's not gaining or losing. So it's neither of these. It's not both of them. It's neither, right? It's not undergoing anything because your number is staying the same. This one, we have another reaction. And in this, it asks what's happening to oxygen and what's happening to the oxidation number of sulfur. So with oxygen, on the reactant side, it is 0. And then after the reaction, it turns into -2. So that is a gain of electrons. So that would be reduction. So it's not A or B. And then talking about sulfur, if we assign some oxidation numbers to sulfur, we'd have -2 on the reactant side. And on the product side, you would end up getting -4 would be +4. So going from -2 to +4, that's an increase of 6 electrons. So we have reduction and 6 electrons. Your answer is D. This next one asking which of these reactions undergo disproportionation. So this is one of those terms that come up. You just have to know it. If you're undergoing disproportionation, you are both an oxidizing agent and a reducing agent. So the easiest way here is to assign oxidation numbers. But what we're looking for is that same atom changing. So I can see it's often going to be chlorine. So just going down to C here. If I went down to C, I see that my chlorine number is 0 or for oxidation. And then on the reactant side, if I assign some, sorry, that should be -2. If I assign some oxidation numbers, I see chlorine would be +1. It's also -1. So anywhere else I'm looking, we don't have the same atom changing. In this case, we do see that same atom changing. So C is showing, and what is undergoing disproportionation is your chlorine atom. Question number 5. So I know I'm going pretty quick here, but if there's any question you want me to do over, just leave me a comment and I can explain it further. So this next one is asking which equations represent redox equations and which one would represent disproportionation. So going through this, I would start by just assigning some oxidation numbers. So if I look at my first reaction, I have chlorine going from -1, and then sodium is +1. We have -2, +1, -2, +1, and that chlorine ends up being +5, and hydrogen is 0. So you do see hydrogen going from +1 to 0. That is a gain of electrons, and you see chlorine going from -1 to +5. That is a loss of electrons. So equation number 1 is a redox reaction. And then we can go down to the next one. So let's just erase the writing here and going back. So we can go to the next one, do the same thing, assign some oxidation numbers, -2, +1, chlorine would have to be +1. On the right-hand side, we put -2, +1, chlorine would be 5, and then we have -1, +1. So we would see in this reaction, chlorine is going from +1 to +5. That is a loss of electrons, and it's going from +1 to -1. That is a gain. So this is also a redox reaction. It also is showing chlorine undergoing disproportionation. So I'm not even going to check the last reaction because I know reaction 1 and 2 both work, and I know reaction 2 is the one that's showing disproportionation. I want to double check that. Yes, and then moving on to the next, we have our reaction here and some information about it, and it says which of the following rows identify the process of carbon undergoing and which type of agent our hydrogen is acting as. So again, all of these are just oxidation numbers. So if you assign your oxidation numbers, carbon would be +2, hydrogen here is 0, and on the right hand side we'll have your fixed numbers, and once you assign your fixed numbers, you'll see that carbon has to be -2. So if you're going from +2 to a -2, you are gaining electrons, so you're undergoing reduction. And then if we look at oxygen, oxygen is going from 0 to +1, so that is a loss of electrons, making it undergo oxidation, and anything that oxidation is your reducing agent. So that is going to be reduction, reducing agent C. One other part just to mention is when you're looking at what's undergoing oxidation, reduction, or which ones are your agents, always pick a reactant. So products help us see what's happening, but it's always the reactants that are undergoing oxidation or reduction. Okay, question number 7, we have again some information, same reaction. We assigned our oxidation numbers already, and it's asking about the total number of electrons transferred. So when we go back up here for a second to the oxidation numbers we've already taken a look at, we see that carbon is going from +2 to -2. That's a difference of 4 electrons. And hydrogen was going from 0 to +1, but each atom was doing that, and then there was 2 altogether, so that's still 4 electrons. So in this one, we should see our answer is B because we have those 4 electrons being transferred. Okay, this one is cellular respiration. More oxidation numbers that we're going to assign, and we'll see, because it is asking what's your oxidizing agent. If you're an oxidizing agent, you're undergoing reduction, so we're going to see what's going to gain electrons. And I can just see right now it's going to be oxygen. If you're not sure, assign all of your numbers, but it wouldn't matter what oxygen you see on the product side. Whichever one you go to, you're gaining 2 electrons. So your O2 would be your oxidizing agent, which makes your answer here A. Okay, so this one we have a series of reactions for the process, and it's asking within these reactions, which ones do your metals lose electrons? So within each compound, if I took a look, I have aluminum within this compound would have a oxidation number of -3, and then it's going to 0. I'm sorry, this was -2. It would have been +3. Then it's going to 0. So that is a gain of electrons, not a loss. So it's not number 1. And I'm only looking at the metal because it's asking about the metal. Looking at the next one, we have -2, +2, and then on the right hand side we have 0. So if we are going from +2 to 0, we're still not gaining, so it's not number 2. Looking at zinc, zinc is going from 0, and then within this compound it's going to be -2. So 0 to -2 is a gain, number 3 works. And then the last one with copper is going from 0, and within this compound here it is -2. So once again, wait a minute. NO3 would be negative. Copper has to be +2. And that is showing a loss. Which one am I doing here? Zinc here. Oh my goodness. Okay, going back for a second because I messed up that explanation. Chlorine forms negative ions, so zinc would be positive. Going from zinc to a more positive number shows a loss. And then the same reason for copper here. Sorry about that. So we are losing, not gaining, by getting more positive. So the answer for this one is 3 and 4, which is D. All right, so this one almost looks like we're going to make a redox table, but we don't need to. When they're asking for the strongest to weakest of your oxidizing agents undergo reduction. So when you're looking at what's happening here in terms of what will gain electrons, your positive charges would want to gain. So the top part here, these are your oxidizing agents. If it's asking from strongest to weakest, if it's strongest, you would look down this column and which one reacts the most. So if I look down the column to see what one reacts the most, your CD2 positive would be number 1. And then you can keep going. So this one had 3 reactions, then the next one had 2 reactions, then just 1, and then none. So our A2 positive would be your weakest. So just looking down, see what reacts the most, has the most check marks, to which reacts the least. And we also want to make sure you can figure out your oxidizing agents. So we know we're not looking at A or B, and the answer here has to be D. Okay. This one though, we are building a table. So in this question, we have some reactions and it's asking what's spontaneous or non-spontaneous. But to determine that, we'll have to build a table based on what we see. So we know based on page 7, if I want to make a table, your strongest OA is top left, your strongest RA is bottom right. If your OA is above your RA, it's a spontaneous reaction. If it's opposite, it's non-spontaneous. So I would start with that first one. I know that M2 positive would want to gain electrons. So that would be an OA, and I can write in this whole thing and show this happening, making M solid. And then the fact that we have products means your RA has to be below it. Oops, sorry. So I put my Q here, and then I could still just fill in my table. I don't need it to. Q positive plus an electron would give you, give you Q. So my RA is higher on the table than my OA. Go to the next one. If Q reacts with X positive, there's no reaction. Q's are already placed. X positive would be an RA. It needs to be below Q to show non-spontaneous. And then that would just give us X. Then the last one is bringing in the Z3 ion. And it has to be higher on the table than M, which is already placed, to have reactants. So I put the Z3 positive up here, add in my 3 electrons, and then I can start adding, I can start interpreting the table. So now if I was taking a look and it's asking what would happen if Z and Q positive reacted, well, Z is here, Q positive is here. That means your OA is lower than your RA. That's going to be non-spontaneous. Now, if M reacted with X, RAs aren't going to react with each other. So that's also non-spontaneous. Then you have your strongest OA reacting with your strongest RA. That's definitely going to be spontaneous. And your last one, you have M reacting with, X positive. That makes your RA higher on the table than your OA. That's a non-spontaneous. So just based on placement, we know which one would be which. Looking at the next one, and we also have some electronegativities, it's asking if we were to look at this data here, what would be your strongest reducing agent? So with these questions, what you want to just double check before you answer is are we showing reduction half reactions? So if we are, it does look like page 7 of your data booklet. And the other part is, are they ordered correctly? And in this case, they are, but they're not always. So just be careful with that. So what you should see is that your cell potentials are going from highest to lowest, which this is happening. As long as it is, you can interpret this table like you would page 7, which means your strongest RA is your bottom right, which makes this the answer being B. Okay, so this one is asking what would give you a spontaneous redox reaction. If you're spontaneous, your OA is higher on the table than your RA. So going through this one for question number 12, if I started with the first one, just finding where zinc was compared to PB, it's going to be my OA. This one, sorry, that looks very messy. I have my OA. This is going to be my RA. Based on placement, my OA is lower than my RA. So if I find it on the table, where with the next one, our OA will be higher on the table than your RA. So if I went to find these two, which are very, very small, we have tin 4 positive, and I'm sure if you're looking at home, you can probably find it way faster than me, and also I don't have glasses on, which is right here. And then lead has to be below it, which is right here. So your OA is higher than your RA, meaning it's spontaneous. So we don't even have to check the rest because that one will be our answer. Well, if you're in the diploma, check the rest just to be thorough. Okay, so then this next one is asking if you can reduce tin 4 positive to tin 2 positive, but you can't reduce tin 2 positive to SN, what is your reducing agent? So I just did a snapshot of the data booklet. Here we have tin 2 positive, 4, and then here we have tin 2. So to be able to reduce to tin 2 positive, we need to have an RA below tin 4 positive. But not to reduce tin 2 positive, we have to have an RA above tin 2 positive. So taking a look at the RAs listed, the one that is in between would be your PB ion. So PB can reduce SN4 positive, but it cannot the other one because that would be non-spontaneous. Okay. Our next one, looking at which ion is capable of reacting spontaneously with our acidified NO2 negative. So with this, our NO2 negative, if you took a look, and I probably should have screenshotted our data booklet one more time, if you took a look at where this would be placed, it would be placed pretty high up on the table. So if you're spontaneously reacting with that, your value for your OA needs to be higher up than your RA. So we're looking for an RA below this 1.52. And the one that will work out is D, your chromium 2 ion. Okay. Our next one, balancing in acidic conditions. For this one, I would split into your 2 half reactions. So I relating with the iodine ion relating to the gas, and then your OCl negative ion relating to your Cl negative. So I would start with either one. So I negative giving you I2, looking at your half reactions. In this case, I can just balance my iodine and then balance electrons, and then that one's done. In the second one, it's a little bit more work. I'm going to have my OCl negative turning into Cl negative. I will add in 1 water molecule to balance out oxygen, and then I'll add in 2 hydrogen ions to balance out the hydrogen, and then lastly balance out the charges. I'll need to add in, so this one's negative, I will just need 1 electron, more than 1, 2, positive 1, I would need 3 electrons to balance out charges, to have a net charge of -1 on each side. Did that work out? I don't think it did. 2 hydrogen. Oh, my dog's starting to cry in the back. Oh, I'm overthinking this. I just needed 2. Okay, so I did all that work, and then just looking at to balance these 2 reactions together, I wouldn't have to do anything because the electrons are already balanced, so we can just add them together. So then the number that's in front of the hydrogen would be just the number you see, which is 2, and then the amount of electrons transferred would be 2. So our answer here was D. Sorry, that one took me a while because it wasn't matching what I had down on my quick key that I did. Okay, looking at numerical response number 2, we have 2 equations, and then it's asking if we have these 2 equations and you're coming up with your reaction, what's your net reaction? So with this, we just want to realize that before we can add these two together, you would have to multiply that second reaction by 2, and then you'll see a few things canceling nicely. So if we multiplied this one by 2, I'd have a 2 here, a 2 here, a 2 here, and a 4 here. So you would see your electrons canceling all together, and you would see 2 of these hydrogens canceling out with 2 of the hydrogens in front of equation number 1. So once you balanced and add them together, the coefficients we would see in front of the oxygen, if you don't see a number, you just write a 1. In front of hydrogen, you'd write a 2 in front of the NADH, and a 2 in front of the water. That's another point just to make here. If you don't have a coefficient in front, know to not fill in 0 because you're going to get it wrong, because that would mean you don't have it present. You must fill in a 1 to have that right. So if there's nothing there, know that there is a 1. Okay, now this next one is similar to what we've talked about before. If we are looking, and this one is asking for your reducing agents from strongest to weakest. So with this, I would note that the top part is all positive. It does get a little bit confusing here because we can see things acting on either side. But if you are a reducing agent here, I was looking, I just wanted to double check here. Yes, it is going to be this side, but again, you can double check based on what's happening within. And then if I'm going from strongest to weakest, for my reducing agents, the one that reacted the most would be that NADH, and then the one that reacted the least would be water. So the one order that shows that is D. Okay. Looking at this one, we have some information of our total reaction, and then said when the incomplete half reaction of NO2 negative going to NO3 is balanced in acidic conditions. So if I was going to do that, I would just quickly balance this half reaction in acidic conditions. And doing that, I could see that nitrogen is already balanced. I need to add in 1 water on the reactant side, but positive twice. Then I would want to add in 2 hydrogens of the ion to balance out the water. And then lastly, I need to balance my charges. So I would just need 1 more electron. I did this on the other one. I don't know why I keep overthinking this now. If I add in just 1 electron, this would be 0. So I need to have 2 electrons on this side. So now that I've done that, then answering the question, water appears as a reactant, and the equation will represent, so if your electrons are on the right hand side, that is oxidation, because you are losing, not gaining. Okay. So now that we have that information, now we're actually doing a calculation, and this calculation is just showing that we know the stoic. So with this one, if we want the concentration of NO2, we can start with the information of MnO4, which is the volume and the concentration, but that volume has to be in liters. So dividing it by 1,000, we get 0.216 liters. Multiplying it by 0.0300 moles, and this would be of the permanganate per 1 liter, so liters cancel. And then we want to use the mole ratio, turning our known into our unknown. So we'll need to put 2 moles of the permanganate in the bottom, 5 moles of the NO2 in the numerator, and then you see your moles of your known canceling. And then lastly, divide by the amount you're using for the sample, but that amount needs to be in liters. Plug that all into your calculator, and you'll see your answer here is D. Now the next one is similar because we're still doing stoic, but we have to come up with the equation ourselves. And you probably did this lab in class, but if not, we can still do it. So you want to see what's reacting. So you have potassium dichromate. So the potassium ion, the dichromate ion, and then you have, it's acidified, so you know you have hydrogen present. You also know you have that tin 2 positive because that's what you're reacting with, and water. Once you have everything present, then you want to look and see what is your strongest OA, and that would be your half reaction for what's undergoing reduction. So I would write out my first half reaction, which would be your chromate ion plus your hydrogens, and you write it down exactly how you see it from the data booklet. And then you would look for your strongest Ra, and your strongest Ra is your tin 2 ion. And looking at that half reaction, you have SN4 positive plus 2 electrons. Then to balance this, you'll need to multiply that second reaction by 3. And if you want, just write out everything again. But if you can kind of take a look at what's happening with your moles, we'll just skip that for a second. The other part here is you want to take a look at your average trials. All of these are within 0.2 of each other, so we can keep each of them. So your average volume is 12.2. So figuring out each of them, so the first one was 12.1, then 12.3, and the last was 12.2. So add the 3 up, divide by 3, and we get 12.2. So I'm going to start with that average volume, but I need it to be in liters. And I'm going to multiply by the concentration of the permanganate, because that's what was the average volume was calculated for. So that would be moles per liter. And then this is the this isn't permanganate, this is dichromate. So I'm now at my moles of dichromate, and I need to turn it into moles of my tin. So it's a 1:3 ratio. So again, if you don't see it right here, just write out your whole equation so it's clearer, but this should be okay. So 3 moles of your tin ion. And then lastly, divide by your sample, which was 20 milliliters or 0.02 liters. Plug that all into your calculator, and it works out nicely to be C. Looking at this one, this is a bit of the theory question on corrosion. So reading it over, it does tell you that your copper was starting to get, I believe it was oxidized. So instead, they are swapping out the iron that was on the copper and putting stainless steel. So then they're asking why. So here it's because the metal most readily oxidized will be iron, right? That's why they're replacing it instead of copper. And what's being oxidized is known as your sacrificial anode. So that is why this one is A. So you do need to know some theory about corrosion, which was usually the last part that you would look at in the electrochem unit. Now moving on to the cells. In this one, we have some information in terms of what's reacting, but it's not telling us what your anode or your cathode is. So if you just quickly took a look at what's reacting, you have copper 2 positive in one half cell with copper solid, and in the other half cell you have an inner electrode carbon, and you have Ag positive. So Ag positive. You do also have NO3 present, but that is just a spectator ion. So based on this information, you would see that what's listed here, that your copper solid is going to be your strongest Ra, and reducing agents undergo oxidation, and that happens at the anode. And your Ag positive will be your strongest OA undergoing reduction, which happens at your cathode. So I know this based on my table that's right here, finding my strongest OA and my strongest Ra. So now if this is my anode, which makes this my cathode, knowing what's happening, your electrons always flow from your anode to your cathode. So going from copper to carbon. So you can rule out A and B here. And then looking at the rest, when it's talking about the directions of anion flow, okay, so this is just our theory question. Anions always flow towards the anode. So they're going to flow towards, okay, it doesn't say that. No, it does. Towards the copper electrode, because that is your anode. So this one is C. Okay, so this next one, we have some information. It does tell you that this is electrolysis, meaning it's non-spontaneous. So right away, without even going here, we know it's non-spontaneous. And it's more of a theory question again, not even looking at the reaction. If it's electrolysis, if you're non-spontaneous, your cell potential is going to be negative. So a bit of a theory question, and the next one I believe is more an application. Or maybe it's not. Okay, so with that, in this equation, it's asking us to now describe what's happening at the anode. So going through this, what do we see here? We're producing 2 rods. Okay, so looking at what's reacting, we're looking at this side here. We are told that both of the rods are made up of graphite. So when it's asking about which one is the anode, well, it is definitely going to be number 1, because we definitely are not seeing any strips of aluminum. Aluminum is being produced, but it's not one of our rods. So that's number 1. So if that is our number 1, then the next one asking, again, it's about the anode. So it's a bit of a theory question. Electrons will move away from it, not towards it. And then anions migrate towards it. That would be number 5. And then lastly, saying it's a site where which one is being produced. Well, if we are producing, or the anode, aluminum is not being produced, because that is what we're essentially plating. So that's happening at the cathode. So this last one has to be 8. So a bit of a theory question, knowing what's going on within the reaction, but also taking into account what you already know about an anode. This one is comparing electrolytic to voltaic. So going through and it's asking which one applies to both. So number 1, oxidation occurs at the anode. That happens in both. Number 2, oxidizing agents react at the cathode. Your oxidizing agent is what undergoes reduction, and that definitely does happen at the cathode. Number 3, cations move through the wire. That's not true. Cations move through the salt bridge. And they move through the electrolyte. That's part of the salt bridge, all in electrolyte towards the cathode. That is true. Number 5, electrons move through the wire to the cathode. That is also true. And then the last 2, electrolytic energy is converted to chemical. That is an example of electrolysis. Chemical making electrical, that is voltaic. So those are very specific to each cell. Okay, our next one here. So in this one, just coming up with that net reaction, you want to take a look at what's reacting. So on one half cell, you have tin 2 positive with tin solid. And then in the other half cell, you have Pb2 positive with Pb solid. Again, your nitrate is going to be a spectator. And then you also see the salt bridge, which is not part of your redox reaction, but it does help the cell move. So then in this one, once you know what's reacting, then looking at your table, you'll find out that tin is your strongest Ra, and Ras undergo oxidation. So that will be your anode. And then your Pb2 positive is your strongest OA, and that would be happening, or that reaction is happening at your cathode. So then the reaction that relates these two and are correctly balanced, I believe, is just B here. So we're looking from tin solid going to 2 positive, not the other ion 4 positive. Okay, this one is talking about a reference half cell. So the theory about reference half cells is that hydrogen was chosen as the reference, and that is 0. If hydrogen was a different reference value, the whole table would shift either up or down to accommodate it. But when it is giving you of a reaction, it doesn't matter what reference half cell you have. If it's asking you for the cell potential is going to be same even if you've changed it, because everything shifts accordingly. So in that case, you would just take a look at your half reactions. So for instance, our chromium here is negative 0.41 and your nickel is negative 0.26. The one that was higher up is your cathode. And then when you do the math, it's always for cell potential, you will have cathode and you subtract your anode. Don't change any signs, plug it in how you see it. So negative 0.26 minus negative 0.41, and you'll see your answer here is A. This next one is asking for the cell potential. So with this one, you want to see what's happening within the cell. So same idea, just write down your half reactions. And then you can look at your cell potential. So this first one is positive 1.07. And then in the second one, we have nickel turning into nickel 2 positive. And this has a value of negative 0.26. So we would see that your cathode was the one that was higher up and your anode was lower. Using that same formula, cathode minus anode, you will get the value 1.33. So again, just looking at the table, finding the placements, your strongest OA is undergoing reduction, which is your cathode. Your strongest RA is undergoing oxidation, and that is your anode. And then your formula is always cathode minus anode. Okay, this one we were looking at what's happening within the cell, and it's telling you we have metal A, and that metal A, well, it's going to be silver. So we have a silver electrode, and if you look at your data booklet, silver is an OA, and that would make that your cathode. And if that is your cathode, then it also has a value of 0.80. Now, the other part here is not telling you the rest, but they are giving you a choice of metals and saying when you put this together, you do get a voltage of 1.20. So if I looked at my other choices of metals, I have nickel, and that gives me negative 0.26. If I go to use the formula and do cathode minus anode, I'm not near this value of 1.20. So I'm going to keep trying. If I look at zinc, I have negative 0.76. So if I do cathode minus anode, I'm getting closer, but we want to check the last one, which is negative, or iron, Fe, which is negative 0.45. And I'm very close to the 1.20 when I do my cell potential. So I can be pretty confident to say that this is iron and this is silver because of what I'm seeing within. So once I have that, then going through filling in the numerical response, saying what's suitable, I would go through and say, okay, my metal A would be 4, my metal B, my electrode, would be silver. Number C, the solution has to have the silver ion, so number 6. And solution D is coming from the salt bridge, and the only salt we have is number 9. So that's what we have there. So once you figure out your cell potentials and the metal used, then the rest is not too bad for a theory question. And the last couple questions have to do with Faraday's constant. So this one is essentially nice and easy. We have the half reaction, and then it's just asking about the moles of electrons transferred. So you'll find that moles of electrons equals your current times time divided by Faraday's constant, but your time has to be in seconds. So you have your 10 amps times 5 hours, but multiply it by this 3600, which if I was using my unit analysis, you'd see your hours turning to seconds, and then divide by the constant, which you can just grab from your data booklet, page 3. And that's all this wants to know. What is your moles of electrons? So plug this in and you'll see your answer here is B. Your next one is a little bit more work just because we do have to look at the half reactions. Whenever you're using Faraday's law, you just need the half reaction of what's being plated or the mass that's being produced. So because this is asking about mass of aluminum, using our half reaction, we know that aluminum 3 positive will need 3 electrons to make aluminum solid. So going from here, what we can figure out is moles of electrons and then turn it into moles of aluminum. Molar mass gets us to the mass. So I would start with moles of electrons. So taking that the amps 5.00 times 10 to the power 4, multiply this by the hours 5.00, and then the same thing times it by 3600 to turn it into seconds, divide it by Faraday's constant. Okay, that gets you moles of electrons. Now I'm just going to keep multiplying. Once I have moles of electrons, I can use the mole ratio to turn those electrons into moles of aluminum. And then lastly, use the molar mass of aluminum, which you're just getting from your periodic table, to get moles of aluminum to cancel and to get to grams. You will get a fairly large number, and you will see your answer is B. So this is all the questions you would get from Quest A+. Again, you can get them for each unit. If that was helpful, please follow my channel, please subscribe. And then I will link this in the description as well. But that is my website that you can go and take a look for specific videos on specific topics in every unit, including unit reviews and practice tests. As always, thank you for watching.